Hello, good evening to you all. You're welcome to our online lesson. Today we are taking an aspect of strand 1, which is number, and substrand 2, which is number operations of our JHS 3 mathematics curriculum. So we are taking an aspect of that called said. Says. So let's look at what sets is all about. When we talk about sets, we are looking at roots of numbers. If I should ask you what is the square root of 9, you all know I am looking for a number times itself to produce the result 9. So if you realize it is the number 3 times 3 will give you 9. So root of 9, you know it is 3. If I ask you of roots of 25, you can easily say it is 5 because you know 5 times 5 is 25. But imagine I ask you the root of 10. You will struggle to get a result because you know 3 times 3 is 9, 4 times 4 is 16. So obviously, the number times itself to give you 10 is in between 3 and 4. But you cannot tell which exact number times itself will produce the result 10. So we see that root of 9 is a set. So when we say sets, we are looking at roots of numbers whose results are not whole numbers. So roots of numbers whose results are not whole numbers. So let's limit our discussion to just square root. When it comes to roots, we have square roots. If I do this, that's square roots. If I do this and then write 3 inside, that is cube root. If I do this and write 4 inside, that is fourth root. So we have square root, we have cube root, we have fourth root, we have fifth root. But we are limiting our discussion on set to just square root. But it can go beyond that. So when we say set, we are looking at square roots whose results are not whole numbers. As simple as that. So if you take square root of 9, because the result is 3, which is a whole number. So we say square root of 9 is not set. If you take the square root of 25, whose result is 5, which is a whole number. So we say square root of 25 is not set. So if you take root of 10, you cannot actually get the definite answer. So we say root of 10 is a set. The first assignment in this video, do it in your jotters or do it on a double sheet of paper. No, just do it in your jotters and then I'll inspect them. Is write down 5 sets that you can think of. Any 5 sets. So I thought of root 10, so don't add root 10. I can think of root 11. Don't add it. I can think of root 6. Don't add it. All of these are sets because you cannot actually get a number times itself to give you 6. And you cannot also get a number times itself to give you 11. So all of these are sets. So now let's move on to the next aspect and the sets. We are now going to look at compound sets and then simple sets. Two types of sets. One is called a compound set and the other is called a simple set. So what is the difference between a simple set and a compound set? When we say simple sets, we are looking at a one-term expression of a set. So square root of 2 is a set. So square root of 2 is a set. And if you watch carefully, you see this is a one-term expression. So that's a simple set. But I can also have square root of 2 plus 1. One square root of 2 would not produce a whole number. If you add 1 to that answer, it will still not produce a whole number. So this is also a set. But realize that this has 2 terms. Once it has 2 terms, we call this one a compound set. So I can have 7 root 3. Now 7 is multiplying root 3. So we can see that this is also a simple set. The compound set will only come in when there are more than one term of the set. So when I say more than one term, we only use plus and minus to differentiate between terms. So once I'm seeing the plus sign here, it tells you root 2 and 1 are two terms. So this becomes a compound set. Once, if I have 7 root 3, there is no plus, there is no minus. They are multiplying, so it's still a simple set. Root 2 is like 1 root 2 or 1 multiplied by root 2. So it's also still a simple set. But if I have, look at this, root 2 plus root 5 minus root 7. This is a compound set because it has three terms. How did I know that this particular set has three terms? I have plus here, I have minus here. The plus is telling me that root 2 is a different term from root 5. And this minus also telling me that root 5 is different from root 7. So in this particular set, I have three terms. So it's a compound set. So any set expression that has one term is a simple set. Any set expression that has three terms, that has more than one term, that is two terms, three terms, and so on and so forth, are compound sets. So for those who cannot spell the single and the compound, the simple and the compound, this is the simple and this is the compound. So this is the simple set. This is the compound set. This is also a compound set. This is also a simple set. So think of getting some examples of simple sets and then compound sets. You take an exercise on that. You'd have to clarify between simple and compound sets. So I will give you an exercise on that where I'll give you about 10 different sets. Then you would categorize them between simple and then compound sets. The next thing we have to look at is reducible sets. So there are some sets which are called reducible sets, and there are some sets which are also called non-reducible sets. Now, how do you differentiate between a reducible set and a non-reducible set? It's very simple. You would have to know the perfect squares, also called square numbers. Square numbers or perfect squares, what are they? They are the results of multiplying a number by itself. So if I'm looking at some perfect squares, 1 times 1 should produce 1. So 1 here, which is the result of 1 times 1, is a perfect square. 2 times 2 will also produce a result of 4. So 4 is also a perfect square or a square number. 3 times 3 will produce a result of 9. So 9 is also a perfect square or a square number. 4 times 4 is 16. So you see, 4 is a perfect square. If I multiply 4 by itself, I also get another perfect square, 16. Likewise, 9 is a perfect square because 3 times 3 is 9. If I also do 9 times 9, which is 81, is also another perfect square. So any number times itself is a perfect square. Now, before we come to reducible sets, let me help you so that we can get the list of at least the first 20 perfect squares in our books. So 1 times 1 is 1, that's the first perfect square. 2 times 2 is 4, second perfect square. 3 times 3 is 9, third perfect square. 4 times 4 is 16, fourth perfect square. 5 times 5 is 25, fifth perfect square. 6 times 6 is 36, sixth perfect square. 7 is 49, seventh perfect square. 8 times 8 is 64, eighth perfect square. 9 is 81, ninth perfect square. 10 is 100, 10th perfect square. 11 is 121, 11th perfect square. 12 is 144, 12 perfect square. 13 is 169. 14 is 196. 15 is 225. 16 is 16. That's the next perfect square. So I think it's I've forgotten a bit. Once you forget a perfect square, you can work it out. 16 times 16. So if you work it out, you are going to have 256. That's the 16 perfect square. 17 is 289. That's the 17 perfect square. Then we go to 18, which is 324, I think. That's the 18 perfect square. You go to 19, which is 361. Then 20, which is 400. So these are the first 20 perfect squares. Now that we know the first 20 perfect squares, we can now learn the reducible sets. So when we are talking about reducible sets, so as I stated earlier, we are looking at square roots of numbers or sets. We are looking at sets which you can divide by a perfect square. The number in the set can be divided by a perfect square. So if that happens, then we say that the set is a reducible set. So what am I talking about? Imagine I have square root of 8 as a set. It's a set because 2 is 4, 3 is 9. So you can not actually get a whole number times itself to give you the result 8. So root of 8 is a perfect square. So root of 8 is a set, sorry. Root of 8 is a set. So if you now know root of 8 is a set, now let's think about it as, is it a reducible set or is a non-reducible set? How would I know? Let me take my perfect squares. Perfect squares in the discussion, please, apart from one, because if you use one can divide any of the numbers in the square root. So you may think that all numbers are reducible sets. So don't use one. With the exception of one, which other square number or perfect square can divide that 8 to that remainder? If you can find one, then it means that root of 8 is the perfect square. Obviously, you know that 4 can divide the 8 without remainder because 4 times 2 is 8. So if 4 can divide the 8 without remainder, then root 8 is a reducible set. I can give you another example as root 11. It's also a set because no number times itself, in fact, no whole number times itself will result in 11. So root 11 is a perfect square. It's a set. Root 11 is a set. Now that you know root 11 is a set, then now, is it a reducible set or a non-reducible set? You test. Can you get any of the perfect squares or square numbers that would divide the 11 and there will be no remainder? No, because the second perfect square is 4. If 11 divides 4, you're going to get 2 and there will be a remainder of 3. If the next perfect square is 9, if 11 divides 9, is 11, if 11 is divided by 9, you're going to get 1 and there will be a remainder of 2. So 11 is 9 2 so perfect square cannot divide 11 without a remainder. Then we can look at the next perfect square, which is 16, way beyond the 11. So we cannot actually get a perfect square or a square number that would divide the 11 and there will be no remainder. Hence, root 11 is a non-reducible set. So that is it for reducible set. Try out this one. Is root 50 a reducible set or not? 4. If you use 4 to divide this, you're going to get 12 and there'll be a remainder of 2. Then you try the next one. If you use 9, 5, 45, and there'll be a remainder of 5. If you use 16, 16 to be 48, and there will be a remainder of 2. If you use 25 to 50, then there will be no remainder. So once 25, which is a perfect square, can divide the 50 without a remainder, then the root 50 is a reducible set. Please note, we are not just using any number to divide the number in the square root, but we're only looking at perfect squares. Once a perfect square can divide it and there will be no remainder, then that set is a reducible set. Is that okay? So I know by now you would be thinking about some more examples of reducible sets. Now let's look at how to reduce the reducible set. Once the set is a reducible set, what it means is that you can reduce it. Once the set is a non-reducible set, what it means is that you cannot reduce it. So now that we know reducible set, let's look at some of them and how to reduce them. So let me take the first example of root 8. Now root 8 is a reducible set. I want to reduce the root 8. And the first thing I have to look out for is, what is the perfect square that can divide our 8 without remainder? That's 4. So now I'm going to see this as root of 4 times, okay, let me take it off. Root 8 should be equal to, I'm going to split. I'm going to first get a perfect square, which is 4. Now that 4 times 4 produces 8, and that's 2. Now after doing this, now if you have two numbers being multiplied within the square root, the feature of the square root is such that you can split them, in the sense that once they are multiplying, I can see them as root 4 times root 2. If I now see them as root 4 times root 2, now root 4 is not a set. Why? Because the 4 is a perfect square. So root 4, we can get a whole number from root 4. So root 4, what number times itself produces 4? That is 2. So root 4 becomes 2. So now you're going to have 2 times root 2. Anytime you are multiplying a whole number by a set, the result is bringing them together. So 2 times root 2 will become 2 root 2. So it means that root 8 is the same as 2 root 2. So the reduced form of root 8 is 2 root 2. Let me take the next example. I'm sure it will bring clarity. So the next example is root 50. If I'm looking at root 50, the first thing is, let me get a perfect square that will multiply a different number to give me 50. We know from what we have discussed previously as 25. Now 25 times what gives you 50 times 2. So now I know the special feature of set. Once they are multiplying within the set, I can split them. So that becomes 25 times root 2. If I now have this as 25 times root 2, and the next thing I have to do is that root 25 is not set. Once root 25 is not set, I can solve it. What time itself will produce the answer 25? That is 5 times 2. Once I do this, bring them together. That's 5 root 2. That's my answer. So root 50 has been reduced to 5 root 2. Let us take more examples of reducible sets. So let's take an example like root 98. Root 98. So once I'm asking you to reduce the said root 98, it means that I'm confirming that that set is a reducible set. So don't think about testing whether it's a reducible set or not. It's already a reducible set. And I'm demanding that you reduce the set. So we just proceed to reduce the set. So we look out for the perfect square that can divide the 90 into that remainder. Obviously, 4 cannot do because 4 times 24 is 96. 4 times 25 is 100. 9 wouldn't do. 9, 10, 90, 9, 11, 99. So 9 wouldn't do. Then 16 to obviously wouldn't do. We test. I know it's 49. 49 will do. So I'm going to see it as root 49. Now 49 times what will produce 98. That's 2. That's 2. So 49 times 2 is root 98. So you split root 49 times root 2. Root 49 is 7. Then we have 7 times root 2. 7 times root 2 is 7 root 2. So root 98 has been reduced to become 7 root 2. Let's take another example. Square root of 27. If we take square root of 27, the first thing, now I'm asking you to reduce it, so you don't think whether it is reducible or not. Obviously, it is reducible. But the first thing to look out for is which of the perfect squares can divide 27 without remainder. Obviously, 4 cannot do because 4, 7, 28, 4, 6, 24. So you try 9. 9 can do because 9, 3, 27. So once 9, 3 is 27, you just write it as such. 9 times 3. So the splitting will work here with 9 times root 3. Root 9 is 3 times root 3. And that should be 3, 3. And that ends it. Okay, so let's take some more examples. Let me take the next one with 72. Okay, so now with 72, you see, we can use 4. Because if we divide that by 4, we're going to get 4 into 7, 1. Remainder of 3, 32. 4 into 32 is 8. So I'm going to get 18. So you can use 4 and 18. So root 4 times 18. Root 4 times root 18. Root 4 is 2 times root 18. And that gives you 2 root 18. Now, this answer is unacceptable. Why? Because the 18 in the square root can also be reduced again. So if you use this approach, you have to reduce the 18 again. So it's not always that when you are getting one perfect square are good to go, like this one. Once you have one perfect square, are not good to go because this root 18 here can also be reduced further. So you go ahead again, leave these two, work on the root 18, and that will be 9 times 2. So root 9 times root 2. And our root 9 is 3 times root 2. and that becomes 2 times 3 root 2. If I multiply my 2 times 3, I'm going to have 6 root 2. Okay, so another way of doing this, someone can also see 9 and 2. We've got 9 and 8, 9, 8, 72. So that person will see the root 72 as root 9 times root 8, right? Which is not wrong. So root 9 is 3 times root 8, and that's 3 root 8. 3 root 8 is also unacceptable. Why? Because our root of 8 is also a reducible set. So we can reduce it further. So leave out this 3. Root 8 becomes root 4 times root 2. And that becomes 2 root 2, right? And that's 3 times 2, 6 root 2. The same answer. So someone else can also see 36. If you watch carefully, 36 times 2 is also 72. So root of 72 becomes root 30. You can go straight away. Root 36 times root 2. So in that case, I'm going to have root of 36 as 6 times root 2. And 6 times root 2 is 6 root 2. So a very clear message here is that you see with one question like with 72, we have 3 perfect squares that can divide 72 without a remainder. Sometimes we have 2 perfect squares that can do that. Sometimes 3 like with 72. Anytime you have more than one perfect square, please do well to use the largest of the perfect squares. It makes your work easier because you only have to reduce it once and you are done. If you use a perfect square, which is the largest, you have to do the reduction more than once. And sometimes if you don't take care, you do it once and you may think you are right. So in other words, also means that when you are done reducing your set, make sure that the answer in the square root is a non-reducible set. So you see, after we are done, root 2 is in the root 2, 2 is in the square root, and that 2 is a non-reducible set. So we are sure that we have reduced the root 72 completely. So in the event where you have a number in the square root, which is a reducible set, it means that you didn't reduce completely. So you can go a step further to reduce what is in the square root, or you can just get to know that you have to start all over again, or there is a larger perfect square that can divide the number in the square root than the one you used. So the choice is yours as to what to do. If you want to reduce and reduce again, it's fine. But to avoid that, just get to know all the perfect squares that can divide your number and then use the largest one. So let me try the last one with 500. Obviously, once I'm seeing 2 zeros, I know there is an element of 100 in there. So with 500, I see it as root 100. 100 times what gives you 500 is 5. What's root 100? 10. 10 times 5 is 10 root 5. And that ends our online math lesson for week 1. I wish you all the best. Bye bye.